Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we did talk about what will happen to a particle, a charged particle moving into a magnetic field, let's say at an angle, of course, yes? We did say that, basically, if it goes perpendicularly into a magnetic field, of course, it will move in a circle. But if it goes parallel into a magnetic field, it will experience no magnetic force, and then in this case, it will continue moving horizontally. But what happens if it moves into a magnetic field at an angle? We said if it moves at an angle, of course, this velocity will be divided into two components. One component is going to be parallel to the magnetic field that will not affect the motion of the charged particle here, so the charged particle will continue, let's say, for that component on a, let's say, horizontal line here. But then we have another component which is going to be perpendicular component to the magnetic field. This perpendicular component causes, let's say, a circular motion here. So we have a parallel component and a perpendicular component. The combination of these two together would cause the particle to move in a shape like this, and this shape, of course, it is called a helical path. So this helical path is due the cause, or let's say due to the charged particle moving into magnetic field at an angle, don't forget. All right, and then of course, we went through these study tips as well, and then we ended up this question right here. So we've solved a question like this, all right, before, but I'm going to solve this one for you one more time, because it is, the idea is very similar to what we have solved before, and then nothing new here. The only thing perhaps is the radius is given, which is nothing new to you, but of course, I'll go through this one, and we will do some conversion as well. Okay. All right, so what do we have here? It says a singly charged positive ion, remember, so we don't have a charge now, we have a positive ion. We don't care what we have, as long as it is charged and it goes into a magnetic field, of course, it can experience a magnetic force, if it is at some angle or perpendicular. Okay, so has a mass of this much, so we do have a mass. Okay, so let's say this is the mass of the ion, which is basically 6.68 multiplied by 10 to the power negative 27 kilograms. Negative 27 kilogram. Okay, that is one. Moves clockwise. So we have a positive charge, and this positive charge is moving clockwise. Okay, so remember we told you, whenever there is, it tells you a positive charge, a negative charge, a proton, an electron, or an electron, whenever they are moving clockwise or counterclockwise, you simply have magnetic force and the direction of the motion as well. So if that is the case, for example, if it moves clockwise, this is clockwise. Okay, so 12, 3, 6, 9, whatever, yeah? Okay, so it moves clockwise. If you take a point right here, for example, at this point, here's the direction of the motion. Or we can take the tangent of this direction. That would be the best in this case, yeah? It is more proper to say. But if you were not drawing the tangent, let's use different color. So here's the direction of the motion, because it is, at this point, it is facing this way. Okay, you do know that. And then because it is moving in a circle, there's always a magnetic force which is directed towards the center of the circle. So this is magnetic force, or the direction of the force, and this is motion. If you have these two directions, can you find the direction of the magnetic field? The answer is yes. It is basically either into or out of the page, if that is the case. Whenever it says something clockwise or counterclockwise, then of course the other component is going to be either into or out of the page. Okay, that is, we're talking about magnetic field and stuff. Okay, on a paper though, or plane of paper, let's say. Clockwise with a speed of, so we do have a speed of, let's go back to the previous color. So we have a speed. What is the speed? Is basically 1 times 10 to the power 4, that is meter per second. Okay, the positively charged ion moves in a circular path that has a radius of, we do have the radius. The radius of this circular path is 3 centimeter. Okay, and of course we're going to convert the centimeter to meter. We can say 0.03 meter. Okay, find the direction and strength of the uniform magnetic field through which the charge is moving. So find B, or the magnitude and the direction as well here. Okay, so watch this. Whenever something is moving in a circle, always remember this, that we have a magnetic force, and of course we have centripetal force as well. Magnetic force equals to QVB, okay, and then Centripetal force equal to mass times velocity or speed squared, you can say, and then divided by the radius here. We're trying to find this b right here. So make b the subject. B equals to what? B equals to mv squared, you can say, and then we can take this qv and q, v, and r. You can see that one of them cancels out with this one here, so we will be left with mv divided by q times the radius. Okay, let's make the radius better. Okay, no, even worse. All right, here's the radius, let's say. So do we have the mass of the ion? Yes. Do we have, what was the mass, by the way? Yes, 6.68 times 10 to the power negative 27. Do we have the speed? Yes. Do we have the charge of that ion? Basically, it says a singly charged positive ion, yeah? So if that is the case, we have one charge, yeah? Okay, and then of course it's going to be 1.6 times 10 to the power negative 9, and we do have the radius. You can find the direction of, the magnitude of the magnetic field strength. That is how you can find the magnitude, and of course it's going to be in Tesla. What about the direction here? So because, let's get back to this one here. This is the direction of the motion, this is the direction of the force. Can you find the direction of the, we have a positive charge, by the way. Can you find the direction of the magnetic field strength? You should. Okay, so once again, hold it this way. Yeah, so tip the palm of your hand, positive charge for electron. We don't have electrons, so focus on the palm of my hand. So watch this. Basically, the force is downward. If I do this, you can see that the motion is basically, the velocity is outward, but that is not the velocity. Yeah? The motion is downward, so the force is correct, but the direction of the motion will have to flip it, yeah? Or you can say switch it. So this is basically the direction of the motion, which is towards the center of the circle, and this is the direction of the motion. So what is the direction of the magnetic field in this case? It is out of the page, you can say, okay? All right. Some more Wrya questions, which I would recommend you to do them. Now, these are basically calculations. We've done questions like this, so I would highly recommend you to do that. I would like to go through this one because it doesn't need any calculation, or perhaps this 3. At which angle between the direction of the uniform magnetic field and a positively charged particle, the movement, the magnetic force on a charged particle is half? Whenever it says half, don't go for 45, no, because we're talking about sine of the angle. Sine 45 doesn't equal to half, no, it is sine 30 equals to half of the maximum here. So in this case, of course, the answer is going to be, let's get it back. So in this case, it's going to be B here. B would be the correct answer here. Of course, there's another calculation here. I'm not going to do this for you. The magnitude of the magnetic force on a charged particle that is moving inside a magnetic field is 0. When is it 0? If the angle between the direction of the particle's velocity and direction of the magnetic field is equal to what? Is it equal to 90? No, it is 90 is maximum, yeah? What about 0? Sine 0 is 0. So in this case, the magnetic field, or you can say the magnetic force, will be 0. Okay. And then what is the path of an electron moving perpendicular to a uniform magnetic field? If it is moving perpendicular, then of course it's going to be a circle. What if it is at an angle less than 90? Then of course it's going to be helical path, yeah? How about like, when will it be horizontal? When will it be horizontal? Of course it's going to be horizontal if the charged particle is moving parallel to the magnetic field direction. Okay, now new concept, okay, which is basically magnetic force on a current carrying a conductor here. Now let me explain this one a little bit to you guys. We've mentioned before that if we have a magnetic field, it could be into the board or out of the board, it doesn't matter. This is just for the sake of the example here. And these are basically supposed to be uniform magnetic field. And we do know that, let's say, if a charged particle is moving whether in this direction or the other direction, it doesn't matter. Imagine, let's say, we have one charged particle that is moving into a magnetic field here. We have a charged particle here moving into a magnetic field, and it is moving upward. The magnetic field is into the page. So what do you think will happen to this charged particle? This charged particle, of course, it will experience a force. So for example, if that is the case, let's say, that is into, here's the direction of the motion, this is a positive charge. So this charged particle would experience a force into this direction here. Let's say a magnetic force. Now, that is for one charge. Yeah? What if we have a bunch of charges? So B, clearly, equals to, or before that, let's write the main equation first. F magnetic for a wire, don't forget, that is going to be BIL. Do I need to use sine theta? No, because that is perpendicular, or if angles are not given, so clearly you don't need that in terms of calculations. Okay, so we want the magnetic field strength here. So B equals to F magnetic over what? Over IL here. So F magnetic force, what is it? That is 4.0 times 10 to the power negative 2 Newton. We don't need the Newton for now. And then divided by the current, which is 22 amperes. 22 amperes multiplied by the length, which is 36 meters. Okay, you do the math, of course, you will get the strength of the magnetic field. That is basically in Tesla. That is that. What about for the direction here? Okay, how do we find the direction? Don't forget, guys, it says the wire is this much. The current is moving from east to west. So let's emphasize on the direction a little bit here. Perhaps I can do it right here. Okay, watch this. So these are the directions, yeah? North, south, east, and west. Okay, how is the current is, let's say, flowing? From east to west. So in this case, we can say the current is moving towards west. That is the direction of the current. Okay. And then if the magnetic force on the wire due to Earth's magnetic field, which is downward or towards the Earth and has a magnitude of this much. So we can say the magnitude of Earth's magnetic field, you can say, or the force is basically downward. By the way, this is going to be, let's say, north and this is south. Downward is going to be something like this, and of course there is perpendicular between these two here. So this is magnetic force, you can say. Or if not, I can do this one, by the way, yes? So let's say this is the direction of the current here, and we can see, I don't know if you can do that or see that or not. So if I hold my hand like this is the current which is going from, let's say, from east to the west, or basically towards west, you can say. From east to west, so basically this is to west, and this is the direction of the magnetic force, which is downward. If that is the case, then what is the direction of the magnetic field strength, by the way, yes? So if I do this, by the way, so let's just flip my hand and make it vertical for a second. If this is the direction of the magnetic, this direction of the current, and this is the direction, imagine this direction of the magnetic force, which is, let's say, into the pitch. If that is the case, then the direction of the magnetic field is going to be upward. If that is the case, you can say north, yeah? So now if I can do this one, I hope you can still see my hand. This is towards west. This is downward, you can say. And of course, my fingers are pointing north. So you can say the magnetic field must be in the north direction, okay? If not, align your hand just like that picture or figure, and of course you'll be able to determine the direction here. Okay, some more Wazari questions. Try to go through them. These are super easy, so that's why I'm not going to do them for you, giving you the chance to practice more on these questions. Okay. Now practice 5e, which is very similar to what we have just solved, yeah? Perhaps I'm not going to do the math for you, I'll just do the direction here. It says a wire carries a current of 7 ampere towards X positive, and the magnetic force, basically, of this much value acts on the wire is in the negative Y direction. Find the magnitude and direction of the magnetic field producing this force in here. Okay, so how about we get, take a look at this one. Watch this. Let's see. By the way, you can do these in many different ways, yeah? So one of the ways, let's do this one right here. It says, okay, that's too much. We want to try to find the direction here. So we're given X and Y and these direction coordinates, yeah? Okay, let's go back to this. Sorry, oops, this is not what I wanted. All right, going back. Okay, so here's X positive, Y positive, and of course these are X negative and then Y negative. Watch this. So wire carries this much. The current is basically towards X positive here. So here's the direction of the current, okay? And then magnetic force this much acts on the wire, and the magnetic force is basically, here's the magnetic force which is towards y negative. Find the magnitude or the direction of the magnetic field, yeah? So remember, the magnitude, you use the equation, but for the direction, I'll do that or help you with this as well. So how are we going to do this one, by the way, yeah? Remember, I can perhaps do this one right away. So this is the direction of the current, yeah? Or you can say proton movement, that is also fine. Okay, and then it says the force is basically directed towards the y negative. So x positive, y negative. What is this direction? Isn't this, that is basically out of the page, or if it is out of the page in terms of coordinates, that is z direction, yeah? But is it z negative or positive? It is going to be z positive because it is outward. So of course we can say the direction of the magnetic field is going to be towards z positive, and then you can use out of the page if given as well. All right, this is the application of the equation, very easy. I'm not going to do this for you. Another question, very similar to the previous questions. Okay, one more question. We've solved this one here. The only idea, take a look, says a thin 1 meter long copper is in a uniform magnetic field and has a massive 50 grams. So don't forget to convert this gram into kilogram. Okay, there is a gram. When the rod, that is basically a metal rod, assuming, carries a current of this much, it floats in the magnetic field. You see, we've said whenever it says balances, cancels, floats, levitate, yeah, these are all means that the magnetic force must be equal to the gravitational force, because gravitational force pull the wire downward, and then magnetic force must be upward so that these two can cancel one another. Okay, so they have to be equal in magnitude but opposite in direction here. So if that is the case, but remember, we don't have a charge like the previous lesson, we've said it before. So we cannot use QVB, okay? Because we don't have a charge. We have a wire in this case. If that is the wire, we use the magnetic force equation related to the wire. So in this case, it's going to be BIL, and of course is equal to mg here. So the mass is given, you do know what is the volley for g, and then the current is given, the length is given, then I assume you can find the magnetic field strength here. Okay, and then of course, that is how it is done. Nothing more than that. Okay, now we'll do one more part because there's an idea in this question here. Okay, what does it say? So also, this one is also interesting because there is one difference between this and the other questions that we've solved before. The difference is not a big deal, but we are still going through this one too. Okay, watch this one here, guys. What does it say? It says a current I, 15 ampere. We have 15 what? 15 amperes. Very good. It says is directed along the positive x-axis, perpendicular to a uniform magnetic field. The conductor experiences a magnetic force per unit length. What does a magnetic force per unit length means? Whenever in physics, whenever it says something per unit something, that means one thing divided by another. So it says force per unit length. Force per unit, that means force divided by the length. So force divided by the length is equal to what? Equal to 0.12. Another indicator to tell what is this, look at the unit. It says Newton per meter. All right, so Newton is basically a unit for force, and meter is a unit for length. So basically force divided by the length. Excuse me. All right, calculate the magnitude and direction of the magnetic field in the region through which the current passes through. So we're trying to find B here. Okay, both magnitude and direction here. So we do know that because we have, where's this? We have a conductor, basically. Let's say whatever the conductor is, that is the same as a wire. Okay, so magnetic force for a wire equal to what? Equal to B I L, yes? But look, okay, it tells you what? We have length or force divided by length in this case, yeah? So we can, or perhaps let's just forget this one for a second. B equals to what? B equals to force divided by the current, let's say, times the length here. So how about if I just switch this to for simplicity? Length times the current. It makes no difference, yeah? But watch this, guys. The question tells you we have, or force per unit length is given. That means this two part together is given to you. In another word, I can rewrite this one here, and of course I can say B equals to what? B equals to force divided by the length, and then of course multiplied by 1 of the current as well. That is also possible, or I can do this one as well. Okay, so what am I going to do now? I'll just find or plug in the numbers here. So B equals to, the force per unit length is basically 0. What? 0.12. 0.12 multiplied by 1 over, what is the current that is given? It is 15, yeah? So multiplied by 1 over 15. You do the math, of course. You'll find the value for B, and that is in Tesla. Now comes the direction, yes? So how about, like, how do we find the direction here? It says the current is basically along the positive x-axis, yeah? So basically this is the direction of the current. That is x or positive x-axis. Okay, to uniform magnetic field experiences this, and okay, so this force is basically in the negative y direction here. Okay, so this is the magnetic force, you can say. So if you have this two, can you find the direction of the magnetic field? You should say yes. So once again, this is the direction of the current, and this is the direction of the magnetic field, magnetic force. So the magnetic field is, let's say, towards the z or positive z direction, because we're given z direction. If you're not given direction coordinates like x, y, z, you can say out of the page. That is also possible. Okay. All right. So you can tell these are basically what we have. Okay. And of course, b times this and all that. You can just find the answer right. Okay. One more thing. Now we did talk about we did talk about a wire inside a magnetic force that experiences a magnetic field that experiences a magnetic force. What happens when we have two wires? Okay, we've also learned before that when we have one wire, and if there is a magnetic, actually, perhaps let's talk about something else. Previously, we did talk about this. When we have a wire, and if this wire carries a current, there will be a magnetic force around this wire. Magnetic field around this wire. Now, so let's say the current is upward. If that is the case, what will be the direction of this magnetic field around this wire? So the direction of the magnetic for a wire, okay, remember, it is not inside a magnetic field. So the current is moving upward, let's say. If that is the case, then, of course, the magnetic field is, let's say this is the pen or the wire. If that is the case, of course, the magnetic field is going to be this way, yeah? Or you can say counterclockwise. It is going to be counterclockwise. And of course, at this side here, it's going to be this way. Okay, because it is moving in concentric circles around the wire. That is basically one wire, okay? Now, what happens when we have another wire? What happens when we have another wire? Let's say we have another wire, same wire, carries the same amount of current as well. So let's call this one I1, and of course there is a magnetic field, B1 for this wire as well, and you can see the length of the wire as well, okay? So now we have another wire. This wire also carries a current. The direction of the current, let's call this one I2, okay? So the direction of this current is still upward, just like this one here. So of course this wire also would produce a magnetic field around the wire. So here's the direction of the magnetic field. Okay, so we said if that is the case, it is the direction of the magnetic field is going to be is going to be counterclockwise. But look what happens on the other side here, guys. Yes. So let me go back one step. So you can see that this was for the previous one. It was, let's say, for this side it was clockwise, but for the other one here, if we go on this, of course, you can see that these two are in opposite directions. So when for example, when the fields are in opposite direction here, what do you think will happen? That means we have two fields, and these two fields are in opposite direction. It's almost like you have north and south, let's say. And if that is the case, then these two wires will pull one another with forces. Let's say, of course, this wire, because we have current one, so we have F1 for wire 1, and of course we have F2 for wire 2. By the way, these two forces, let's say, if they carry the same amount of current, if we have, let's say, the same wire and cases, so these two forces will be equal in magnitude but opposite in direction. But there is one thing I want you to be very careful with, okay? So, but watch this. If we have one wire alone at this point here, Okay, so of course there is a current, there is a magnetic field, yes, but will there be any forces pulling or pushing, let's say, the wire? Will this wire be exerted or under the influence of any forces? If it is not close to any magnetic field or wires, the answer is no. But what happens if we put this wire into magnetic field? Of course, it will experience a force here. Now imagine instead of having this wire inside a magnetic field, let's say. Now this magnetic field that we have, it is going to be this magnetic field that we have is basically provided by this wire in this case. So if that is the case, then of course we will get a force on the wire because it is assumed that this wire is inside this magnetic field. Okay? This magnetic field is basically, you can say something close to this is provided by the second wire, the second current carrying wire. But you can see that this magnetic field will be perpendicular to this wire. So of course each one of these wires, or let me say this. So of course the wire that, or the force that we get, it is due to this field here. So of course we get a force, or we will have a force, but this force would not happen if we did not have this magnetic field. So if we want to find the force on the first wire, we're going to write this. F1 equals to, remember, BIL. So these are for current 1, for L1 you can say, but this magnetic field, where does it come from? Like what magnetic field causes this wire, for example, to experience a force? That is this wire right here. It's almost like this wire is inside that magnetic field. Remember, this magnetic field, it is not induced by this one here, okay? It is not, let's say this is wire 1, okay? This is length 1 as well. So this magnetic field, it is induced by the second wire here. So I can call this one B2 because it is caused by wire 2. So this is my bad. This is B2, and we can call this one B1, of course, yeah? So the force that acts on the wire, we cannot say B1 because this magnetic field, it cannot cause a force on the wire itself, okay? So, but this magnetic field would cause a force on this one. So of course we're going to use B2 here. Let's make it red so it is more obvious. Red, it is more obvious. Okay. So F1 equals to B2, I1, L1. What about the force on the second wire? The force on the second wire, it has something similar to this. So we can say F2 equals to B, but I won't tell you which one, times I times L. So these are I to L2, yeah? So this B here, remember now, imagine this time, this wire is inside a magnetic field that is provided by this one. So of course we're going to use B1 here. So I want you to remember this. These two forces are equal in magnitude but opposite in direction here. So we can say the force on this wire is provided by the magnetic field of the other wire, and the force on this wire, let's say provided, or you can say the magnetic field of the other wire provides, or you can say cause this force on this wire right here. So, by the way, don't forget, if the current in the two wire were in the same direction, they will always attract one another. So these two forces are attractive, but if one of them, or if the current were in opposite direction, then they would repel one another. And let me tell you why they would repel one another if the current in the two wire were in opposite direction here. So let's go through this one more time real quick. So let's say here's one of the wires, okay, and this is the second wire. Imagine if the current in the two wires were in opposite. So one of them the current is into, and then the other one is basically the current is, let's say this one is moving upward, this one is moving downward. So we said I'll just draw one circle here for simplicity. So if that is the case, the current, if this is the wire, you can see, so here's the direction of the magnetic field, okay? So basically counterclockwise. But for the second one here, because the current is moving downward, so if that is the case, so the current or the direction of the magnetic field is going to be this way here. So if I draw this one here, okay, you can see that here is going to be the direction of the, let's make it blue so you can see, oh, not this one, sorry. Okay, so this is going to be, let's choose, yes. So here is going to be the direction of the magnetic field. So it's almost like you have two magnetic fields that are equal, or you can say same direction. If that is the same direction, it's almost like you have north and north, or south and south. So if that is the case, then of course these two wires will repel one another. Okay, so if the current in the two wire were in the same direction, they would attract one another. What if they say, instead of saying the current is the same, what if they say the positive charges moving are in the same direction? What if they were saying the electrons in the two wires are in the same direction? These all mean the same thing. That means the current in the two are the same direction. But be very careful here. What if they tell you, for example, the current in one wire is, let's say, upward, and then the electron movement in the second wire is also upward. If that is the case, remember these two would be in opposite direction, because one of them, it talks about the direction of the current, which is upward, and then the other one, it talks about the direction of the electron. Electron and current are always moving in opposite direction here. So this is all about this, and I hope that was clear enough. So this is basically the detail of what I just have told you. These two forces are equal in magnitude, you can say, but opposite in. If that is the case, of course, these are attractive. You can say opposite in direction. Okay. So study tip, watch this. It says what? If the current, or if currents in the two wire have the same direction, the two wires will attract one another. Okay. And if the current in the two wires have different direction, the two wires repel one another. The above can be confirmed using the right-hand rule, like just what we have done. Explain why two parallel wires carrying current in opposite direction repel each other. That is, the answer is because each wire produces a magnetic field around the wire, let's say circular, of course, magnetic fields around the wire, which is perpendicular to the other wire at all times, you can say, or points, not times. When the current are in opposite directions, these magnetic fields, of course, oppose one another between the two wires. This opposition creates a force that pushes the wires apart, causing them to repel. Okay, this is basically just like the drawing of, simplify this one in a second. All right, take a look. Let's see if we can solve these 3 questions. All right, take a look. Perhaps maybe only 18 would be enough for now. But let's solve this one and see how it is done. If you understand this, perhaps, or how it is done, perhaps that means you've understood this fully, and that would be a great thing. If not, please, or I would recommend you to re-watch this one and practice more. It says, a stream of electrons, watch this, so we have electrons now. A stream of electrons are projected horizontally to the right. A straight conductor carrying current is supported parallel to and above to the electron stream. Okay, so we have, let's say, a conductor, and of course, let's say we have, let's change this one as well. So, oops. Let's see if we can do this one. Let's erase this one for now. Okay, now watch this. What does it say? It says a stream of electrons is projected horizontally to the right. So this is basically to the right. These are, let's say, a stream of electrons. So electrons are moving to the right. Okay, electrons are moving to the right. Okay. And then it says a straight conductor's carrying current is supported parallel to and above the electron. So parallel to, these two are parallel. So here's the two, let's say, conductor, just parallel to this, but above the stream of electron. Okay. What is the effect of the electron stream if the current in the conductor is left to right? So once again, what is the effect on the electrons if the current on the electron stream, of course, if the current on the conductor is left to right? So of course, if that is the case, watch this. What would happen if this is the direction of the current? Basically, they tell you, will the two attract or repel one another? So watch this, guys. We said if the current in the two wire are in the same direction, they attract. If it is in opposite direction, they repel. Watch this. If you consider this one, this direction of the electron, the direction of the electron and the direction of the electrons are equal. Can we say they attract to another? No. Why? Because we said the direction of the current is always opposite to the direction of the electron. So if electrons are going to the right, then the current is to the left. So we have current going to the right, and so the direction of the current in the two wires are opposite. If they are opposite, then of course these two would repel one another. Or you can say this conductor would cause the electron beam to shift because they would repel one another. Or you can say in this case it shifts downward, yeah? So indicating that these two would repel one another. What is the effect of if the current is reversed? If the current is reversed, watch this. When we say the current, we're talking about the direction of the current in the wire, yes? Although remove too much. Okay, so what if the current is reversed? If the current is moving this direction, the current of the stream electron is in this direction, then of course these two would attract one another. Okay, so the first case, or for part A, they both repel one another. Okay, for part B, of course, they attract one another. So the beam will move away to the wire, that was the first case, and then for the second case, the beam will move closer because they will attract one another. Now, for question 19 says, if the conductor in question 18 is replaced by a magnet with a downward magnetic field, what is the effect on the electron beam? All right, so take a look. Let's say now we are replacing the above conductor with a magnet. So let's say this is a magnet now, and this is north, because the magnetic field lines are basically downward. If that is the case, watch this, guys. We have the direction of the current, we have the direction of the magnetic field, B, okay? If that is the case, what do you think will happen to the stream of the electrons? Of course, there will be a force on it, but can you tell which direction, or what will be the direction? I hope the answer is yes. So remember this, that is the direction of the magnetic field, yeah? This is the direction supposed to be of the current, but you can see it's opposite direction, so I'll flip it this way, yeah? If that is the case, watch this, direction of current, direction of the magnetic field. So in this case, you can say the stream of the electrons there would be a force on it, which makes it move out of the page, you can say, or move in positive Z direction here. All right, so the electron beam will move out of the beam towards the positive Z direction. Okay, and I believe, let's see if we can keep this one. Yes, I don't know if we have, okay, take a look, guys. The last thing for this session is what happens when two wires carrying equal but opposite currents are twisted together, let's say in the construction of a circuit. Why does this technique reduces any magnetic fields here? Okay, now watch this. This is something very important. We've mentioned earlier that if we have a wire, if this wire carries a current, of course there will be a magnetic field around it, yeah? So let's say here is a wire, let's make it vertical so it is more obvious. So if there's a wire, there is a current in it, there will be a magnetic field around it, yeah? So what happens when we have two wires, and each one of these two wires, of course, there is a, let's say, there is a current carrying, for example, there's a current in each one of these two wires. Of course, there will be a magnetic field around each two wire, and of course, at this point, they would repel one another, yes? Because there's a magnetic field in between. So, but what happens when we have, for example, two wires, but these two wires, let's say, are, you know, like, connected, or you can say tied this way. Not a perfect one. You can take a look at this one to understand what I'm twisted wire, yeah? To understand more what I'm saying here. So by doing this, you can say here, or you can say the magnetic field of one of them here. So there will be almost like no magnetic fields in between the wires, not even outside. Why? Because we can say the magnetic field of these let's say wires will cancel one another, so there will be no magnetic field around the wires. What is the purpose of this? Sometimes, of course, having a magnetic field would cause, let's say, damage, especially if it is electronic circuits, and if you have wires there, maybe there will be a magnetic field. This magnetic field could, let's say, cause some damage to the processor, to the memory, whatever. It doesn't matter whichever the part is, yeah? This let's say magnetic fields around the wire could cause problems, so we try at some points, it would be best if we can eliminate them the most. So by doing this, of course, we can get rid of most of the magnetic fields around the two wires. That would be the purpose simply. So why? Okay, because the two wires are twisted together, so the magnetic field are opposite, cancel one another, so that the area occupied by the remaining magnetic field would be very, very small. So that was the purpose of all this. And of course, we have these two exotic questions. I would recommend you try to do them. Next time, inshallah, we'll continue from the application of the magnetic force on a carrying wire, or using a speaker, basically. Till then, keep practicing, and I'll see you soon. Assalamu alaikum wa rahmatullah.